Okay, I think we're going to go ahead and get started. So welcome to another session of Nano at Tech. Before I introduce today's speaker, just a quick scheduling note. So our normal scheduled next seminar would be on February 24th, 2 weeks from today. But because of a conflict with an IBB distinguished lecture, we're going to postpone that seminar for the fall. So there will be no seminar on February 24th here. Our next Nano at Tech seminar will be on, I'm sorry, January 24th. Our next Nano at Tech seminar will be on February 7th. So you'll see the emails about that. So it's a real pleasure to have with us today Professor Julene Tong. Professor Tong did her undergraduate work in chemical engineering at Changsha University of Science and Technology in China, and then a master's degree at Tianjin University of Science and Technology before coming to Georgia Tech, where she got her PhD also in chemical engineering, and then worked for 2 years at CH2M Hill, a engineering consulting company, before moving to the University of Florida Department of Agricultural and Biological Engineering, and then finally coming back to Georgia Tech last year in 2022, where she is currently an associate professor of chemical and biological engineering. And with that, I will say welcome back to Georgia Tech and turn it over to you.
Hello? Okay. Thanks for the nice introduction. As mentioned during my short introduction, my work will mainly focus on, you will see applications in agriculture or animal or food safety, because like during the last several years, I was working in the different department, different from the engineering school. So today, it's my honor to talk about my research, self-assembly of bioresources materials for functional nanomaterials. So when we start talking about sustainability, we usually consider like many environment informations, like population change, climate decarbonization. You can see all these buzzwords, water nutrient recycling, water energy food nanics, renewable energy, and also food safety, nutrification, greenhouse gas warming, all these problems. So, but what we just thinking about is like, if we deal with that, firstly, we deal with the limited resources, and also for the pollution, we produce a lot of waste. So what I'm trying to do is like, how can we convert this waste to resources? And then we can make the value-added bioproducts, chemicals, materials and fuels, so that can be reutilized, and then we can reduce our problem for the limited resources. That's what I'm focused on. So I usually use this figure to show you like what I'm doing. So my mission, research mission, is like we try to efficiently utilize of the limited resources and bio-based waste. So from different sources, so you can see either from industry, agriculture, and all other natural resources. So we can convert this bio-waste to bioproducts. So then finally we can achieve towards the beneficial circular bioeconomy. That's my purpose. So anyway, we mainly focus on there are many different types of the waste, like in like cars, like steels, but what we mainly focus is bio-based waste, because we trying to form the nice cycle. So after application, we still can, these materials, chemicals, and these things is degradation, after degradation, they can come back to our nature again. So forms a nice closed cycle. That's our purpose. As I mentioned, my group also working on the biochemicals and biofuels, smart biomaterials, sustainable agriculture, and plastic recycling. But anyway, today I will mainly focus on the how can we use the nanotechnology, nanoscale and nanoscale self-assembling so we can make the smart materials from the bio-based waste. So if we look at the waste, so as shown in this figure, United States generates the most solid waste, about 6 million metric tons per day, 0.6 million metric tons per day, solid waste per day. And also, if we look at, as we say that we want to convert this waste to the bio-based resources. So if we look at where bio-based resources come from, so it can come from the solid waste. We know like DOE really focus on that, like fractionation and reutilize the solid waste. And then we also look at the forestry croppers and residues and agricultural crops and residues. So my group has done a lot of work we can do, like using the agricultural crops and residues, so we can gather the smart materials, so then we can benefit the agriculture, sustainable agriculture as well. And also there are other like industrial residues, like biorefinery residues. I will talk about the lignin and glycerol as residues. How can we convert it to the bio-based smart materials, and sewage or wastewater. So sometimes we needed to recover the nutrients from the wastewater, or we got the biodegradable, sustainable, smart materials. We can recycle this waste, and then this waste can be using as a nutrients for agriculture, for crop growth, and then for food safety. So here I just want to show different type of the bio-based resources we can separate it with. First one is forestry slushes, wood and agricultural food. For example, the skins for the fruit. For example, I will talking about the peanut shell residues and animal feathers. We use this one as a coating materials for the snow release fertilizer, and also all these different kind of the lignocellulose, like biomass from the forestry and agricultural residues, so we can make it biochemicals and others from here. And also another type of the paper and the packaging products. So here, recently, because of the COVID, so we ship a lot online, so we got a lot of packaging materials. And also, if you look at solid waste, actually about 40% of that is this packaging materials, actually, right now, in recent days. And the textiles, and also plastics, also in solid waste or other recycling sources, and also industrial residues. For example, I will mainly focus on like biodiesel process. They have glycerol occupy 1/3 of the waste material, and also from the pulp and paper mill, and also from biorefinery sources, you got the lignin. Right now, they are just burn it as a energy. So how can we convert it to the value-added materials? And also others from ocean, like chitin. So what's the challenges if we want to use nano self-assembling to make materials from these bio-based materials? If you look at the structure of these biomoleculars, like cellulose, they are linear polymers, but they have a high degree of the polymerization, about 15,000 degree of that. So it's very hard to macromolecular structures. It's not small materials. And for example, the lignin, they have a cross-linking structure. So depending on different type of sources, different extraction process, So you can get all different kind of heterogeneous properties. So some of them, they can soluble in the water. Some of them, they cannot soluble in any organosolvent or water. So, and also if you deal with the waste materials, you need to thinking about disturbance of the impurities. That's what we faced on recently. And I want to use the wood as an example. So to show you like wood loggers and timber, you can see it's meter size. Sorry. So it's a meter size, right? So when you disintegrated this cell wall structure, so you can got the cellulose fibers is millimeter, and also they have high aspect ratio. So maybe diameter is about nano size. And if you remove the amorphous phase of the cellulose, so you got the nanocellulose, and this one you have high aspect ratio, but anyway, you got the diameter definitely in nanometer size, or maybe length also nanometer size. And then you further degrade to the nanometer ions, so you can get dissolved cellulose. So you can make the liquid crystal from cellulose. So you can see, so this is like one example. We scale down the size. So why nano? So if we look at the cell wall structure, so cell wall structure actually, if you're trying to use the waste, like agricultural waste and forestry waste, so you must firstly destructure this structure. But for the biomass structure, cellulose is the most valuable and also the most abundant materials in nature. But anyway, they linked together by covalent bonding with lignin and hemicellulose. So firstly, you need to remove these two materials so you can get the cellulose fibers. But if you look at the cellulose fibers, they are binding together because like for wood, they need this, we against the nature, because if we want to downsize the cellulose fibers, so firstly they are consistent of the microfiber bonders, and then you can further downsize microfibers and elementary fibrils, and then finally the cellulose chains. So you can get like 5 nanometers. But here all this needs the energy, harsh reaction conditions to get these materials. So you only in the lab or currently people do is like firstly using the enzyme or chemicals and thermal way, so you can get the microfabricated cellulose. Or if you further use the harsh conditions, you can remove the amorphous side of cellulose, so you can get the nanocrystal cellulose. So as we say, why nano? So if you look at this figure, so this is published in like 1997, people found like cellulose crystallize, so they have high specific tensile strength, about 140 gigapascal. So even is close to the E-glass and much higher than steel. And also, another beauty thing about nanocellulose is like, except they have high specific surface area, they also have high aspect ratio. That means like if you thinking about the same properties, same strengths, if you have high special aspect ratio, so you need use less materials. So it's much lighter, but much higher strength you can get. You can, if you got a cellulose crystalline, so you can get really high strength materials. So that's like you can use for the airplane, car. So that's very good for cellulose. So okay, I mean this is just like some introduction about why we use nano materials, why we want to use the waste materials. So later on, I will use several examples to show what we use the bio waste materials for a different project. The first one I want to talk about is like we started with the biorefinery residues. So this cellulose, I mean, you can see it's a brown color, so they have a lot of lignin inside. So we're starting from these materials, so we can make the nice hydrogel. So the method we use, like we can remove the delignification, but we don't cut the cellulose length too much, so we can form the non-fiber. We believe that one can give our data showing that the hydrogel have better strength for that. And starting with this is like some work we published like a long time ago. So we made a hydrogel with like a high strength, and also we using the called the PLA, PDMA, EMA, depends on different molecular structure of the PLA and the PDMA, EMA. Like PLA is like harder part, PDMA, EMA is softer part. So we can make the transparent film, but these films property, depending on how can we tune this copolymer structure, so we can tune their strength, we can tune their plastic and elastic and plastic properties based on the molecular structure of these materials. And then further on, as we mentioned, based on this hydrogel, we further using the nanocellulose make the called the injectable hydrogel. So we functionize, we firstly got the CMC, and then we functionize this cellulose as CHO and NH2 groups, grafting these groups at the end. And also, this research is mainly firstly cellulose, long fiber cellulose as a starting material, so we can, using the shift-based reaction, we can form the injectable gel. I think it's a few seconds, less than 10 seconds. We can adjust by adjust the this grafting. Oh, sorry. I think this doesn't work anymore. That's fine. So I mean, based on this, tune these ender groups, so we can make the injectable gel really injectable, and they can form the gel in 10 seconds. And also another copolymer we used, so they can, outside is the micelle structure is hydrophilic, so they can be put in one of our cellulose solutions. And the second one is the the inside core is the hydrophobic, so we can encapsulate the hydrophobic drugs inside. So then we can form the double layer to achieve the a slow release of the hydrophobic drugs control and pH sensitive release of the hydrophobic drugs, but also injectable hydrogel based on cellulose. Okay, another work I would to talking about is like our work. We have done this research for several years, and 2 graduate PhD students. So we're starting from the glycerol as a starting materials. So, and firstly, we trying to got a really highly pH sensitive biofilm by nano-encapsulation, and then trying to make devices that can detect the food quantity, but the no-cost materials. So firstly, this is showing the basic concept. So we, for this research, we aim to develop a real-time, simple, and user-friendly food freshness detection systems that can combining like our sensory film and also the machine learning technologies together, so to detect the food spoilage. So firstly, let's talking about why we need highly pH sensitive film for food spoilage detection. So recently, the food spoilage detection mainly either you need to know the bacterial or the chemical structure, so then you can test the detect the bacterials or the volatile organic compounds. But this is time-consuming and expensive. Industry uses the polymerase chain reactions. It's really time-consuming as well. So what we're trying to do is like originally our idea is trying to make a food packaging film. So it can be used as food packaging film, but at the same time they can rapidly detect the food spoilage with immediate contact to consumers. So our materials must to be food safe, and also we found that if you see the current publications, people use like cellulose, chitosan, or maybe starch to make the pH sensitive film. Firstly, maybe it's hydrophobic, and secondly, they cannot detect the pH within very small range. So, but our film, we can make the range less than 0.2, and then so finally we want to get this highly pH sensitive film, but anyway, it's hydrophobic and food safe. So the first thing, we're starting from the glycerol. So using glycerol starting materials, so first you make the hydrophobic, add the double bond on this glycerol, and then react with ammonia, so we can form the micromonomers. So they have pH sensitivity, but anyway, it's hydrophobic, and also they have double bonds. They can form the polymers when we do the nano-encapsulation. And the second step is like we encapsulated food safety dye inside this using we call it the mini emulsion polymerization. So we're trying to mini emulsion polymerization. The mechanism is like they can achieve the nano-encapsulation. So and also make sure that you have one-to-one copy before your polymerization and after polymerization. And because we have the diamine reactor with diamine, so our surface is pH sensitive as well. So then and also, we mentioned that we want to get this precise pH-sensitive biofilm. So we can adjust our nanoshell structure. So then we can achieve we can control the dye release rate. So then we can detect the pH sensitivity. So here is showing our results. From here, you can see pH 7. pH 7, you can see we got 100 nanometer particles, and after pH 5.4, so you can see this little dots is the dye release out. So here you can see the pH. This is showing like a different kind of the dendrimer as a coating materials. What is the particle size change, and also the fluorescence is showing like we can control the pH 0.5, at least 0.5, we can see the difference. So it's very sensitive, and the right-hand side is showing like the thermomechanical properties and this the hydrophobicity. So that is can be used for the food packaging. So here is just like a kind of animation showing how can we control this pH-triggered dye release, okay? Later on, after that, so firstly we make the packaging film. So our film can be contact with the food, and also we also found that we use fish as a model, showing that even we don't contact with the food as a VOC, we also can detect the VOC as well. So then the next step, what we do is like we use we call it the surface imaging and machine learning approaches linked with our sensor film to detect the food spoilage. What we do is like we make called the QR code. So we put the make the QR code, put our sensor film in the center, and then in the three corner we have standard corner. So when they contact the food or detect the VOC, so we can make sure we got the information we have, the imaging information we have. We can just use a cell phone to get the image. So this, and then, so because they're highly sensitive, pH sensitive, and also, I mean, this is our sensory film put in the center. So then you can just like scan it, so you can get all this corner information based on the food spoilage. So then we using, it's called the K-nearness label algorithm. So my student did the experiment. So we used the pork lion as a model food. So we put our film on the food, and then we got a lot of videos, and then we analyzed these videos, and then using the machine learning method, so got these pictures. So this is called the so you can see. So then we can detect like this red one is the red one is the spoilage one. The blue one is the good quality food. So anyway, if you use machine learning models, so only our experiment data is not enough. So we also add some like data from literature, and also we use the we also because for the pork the pH range is very small, it's to 4 to 7. We also use like other food models, like trying to generalize this method as well. So if you look at the final products we got, so what we need is just like a cell phone. You have pre-loaded data based on database, and also what we do is like we can load it our sensor film with a QR code. So, but anyway, compare with the existing product, actually this is Amazon showing like they have share some like you can purchase a spectrometer. So, and with the analyst app, so then you can determine the food quantity, and also you can, you can scan food directly, but anyway, it's expensive and limited functionality. So it's only 2.7 stars on Amazon. I think maybe already off the market recently. But our method, we can achieve the fast detection. So in one scan, we can get all the necessary information. As if we combine with the QR code, you can also get like what's the date, all the information for the food, and also reliable results, because we use the background and the lightning correction as well, and user-friendly, and you have all the detailed information as well. Okay, so this is like another example. We use like a glycerol, which is like a low-cost and bio-waste material, starting material for the food packaging. So another example I want to talk about is like using nano-Chitosan or alginate nanoparticles loaded with lactamase for multiple drug-resistant pathogen resistance. I think this research is like I collaborated with University of Florida animal science professors. We got the USDA grant and work on this project. So firstly, I want to give a little bit of background. Antibiotic resistance pathogens results a lot of at least 3 million infections and 36,000 deaths annually in the United States. So among all these APRs, so one type that causes serious threat to public health is called this one, extended spectrum beta-lactamase, called the ESBL. So they can produce in the pathogens, but anyway, ESBL producing pathogen has like confers resistance to many common used antibiotics. So we needed to develop a new combination theory for multiple drug resistance, resistant like this ESBL pathogens using the chitosan and alginate nanoparticles loaded with antibiotics and beta-lactamase inhibitors. So the challenge for this work is like, I mean, we trying to encapsulate these antibiotics and inhibitors for these pathogens, especially for these pathogens. So then we can allow these antibiotics can release to the loading area, so then they can kill these bacteria. So of course, because this method, these nanodrugs we got, we need to use for the cow, really use for the cow, so definitely need to be food safe. So that's the reason all the material we use, chitosan, alginate, or all the chemical we use for, like, for example, we use the vegetable oil in our water oil nano-encapsulation systems as well. So need to be safe. So, I mean, so the first challenge we met is because inhibitors and these antibiotics, some of hydrophilic, some of hydrophobic. So what we do is, like, we firstly use vegetable oil to encapsulate, coated on the inhibitors and these antibiotics, and then further we dissolve in an emulsion, make an emulsion using the nano-chitosan or nano-alginate. So then we found, this is showing, like, we found the double layers. We found the double layers right here. And then, so we use the water oil, water mass emulsion system is chosen for this study. So we successfully encapsulated, like, two antibodies, like, and two inhibitors. And so this data is showing, like, they can efficiently kill the antimicrobial resistance bacteria within 6 hours. So this SEM picture showing, like, this bacterial cells can be damaged, and this work is showing, like, our material doesn't cause the toxicity using these elegans as an example. So there are several papers based on that. So, and we also compare with the chitosan and alginate, because chitosan itself is antibacterial. And then we recognize that chitosan, the problem is you disperse it, you need to use the acid. So then if you, mostly this work is like very similar with each other, but the alginate can give much higher loading efficiency, encapsulation efficiency. That's important because these drugs, inhibitors, and antibiotics is very expensive. And also don't require the acid as well. So here is just showing, like, we can show, like, high loading efficiency, excellent antibacterial properties, reduce the toxicity and the nest cell toxicity as well. So both chitosan, nano-chitosan, and nano-alginate works. Because, I mean, you know, USDA, we got funding from the nanotechnology. So you must show the picture during your project. So you must to have your particles within, like, less than 100 nanometers. I think we spend a lot of time to do that. Actually, it really not affect our property that much. So, yeah. Okay, I think we still have a little bit time, 10 minutes. So I may show another work. I mean, this is just one work we did. So as I mentioned before, recently I have been using, like, lignin and agricultural residues to make a lot of materials that can either, we can recovery like phosphorate and nitrate from wastewater, so then we can recycle back, make the as a fertilizer or nutrients for the crop growth. So I mean, this trying to make a circular economy works, closed cycle. But anyway, this work is a little bit different. So this study is like we really use, like, a lignin as starting material, so we make called the lignin nano-clay hybrid. And this one, even like, we can trace it as my PhD study. So actually we use this nanohybrid, non-lignin-based, nano-clay hybrid, so we can make the food packaging film. So I just make a lignin nano-clay hybrid. So they have two functions. First function is they can, as a coating material, these nanomaterials, they can block the urea release out from the control release fertilizer as a coating material. And the second one is they have absorbance to the some nutrients in the soil. So we're trying to make this double function nano-coating materials. And also accept this nanohybrid. So another coating material we do is we liquefied the agricultural residues, no matter what. If you have some stains from your agricultural residues, so you can directly use liquefied it, and then you can make the bio-based polyurethane. So combined with this nanohybrid together as a coating material, so to make the control released fertilizer. So I mean, firstly, I want to explain why we use the lignin, because they are most abundant aromatic resources, so they can reclaim from waste streams and also from solid waste. And recently, we have another project using the lignin from solid waste to make the jet fuel. So, and also the big problem is they have huge production, but right now only 2% of lignin has been using as advanced materials in their limited market existed as well. So here is just showing you can see this is our nano-lignin clay hybrid. The size is about 200 nanometer. So what we do is firstly we synthesize quantitative lignin, and then with the anionic clay together, so they can insert from the exfoliated nanohybrid structure. It looks like a gel-like structure. And the second step, as we mentioned before, we combined with the agricultural residue-based bio-based polyurethane together, and they encapsulate the urea inside. So here is showing the pictures with the nanohybrid. You can see we can get the rough surface, and also you can see the pinkles just getting less and less. So because that's important. So if you can control the urea release, so you can definitely you can adjust your nutrients based on the plant growth period, and also you can reduce the pollutions. Nitrogen goes to the soil and water, and then it's benefit for we know the nitrate oxide, it will affect the climate warming, result serious global warming issues. And here is showing I mean, as I mentioned that the materials we made not only for snow release, but also bio-based sustainable snow release, but also we can so copper, zinc, iron, there are some metals in the soil, so the nutrients, so we can absorb these nutrients, can be used by the croppers as well. Here is showing one of my students using the radish as a plant. So they look at firstly we look at the nitrogen release rate. You can definitely see with this nanohybrid include, so they can significantly reduce the nitrogen reduce rate. So, and also, I mean, you can see even 30 days. So 20 days, so definitely good snow release. And here is showing some leaves and root shoot ratio is showing it's significantly, you can see this tree looks more leaves and much better condition than this one as a control. So that is what we do. So different examples for nano assembling we do. So here it's like I just want to use this slides to show you like what do we do. So this is resources as we say that like we use the peanut shell, we use the nano-Chitosan, and we use the agricultural residues like glycerol and also solid waste like forestry residues. So through the nanoscale self-assembling, either like nano capsules or co-shell, like that mini motion polymerization is co-shell structures. So got the smart materials, and also we do the molecular self-assembling as well. So the application right now, we focus on the agriculture, food, and environment utilizations. For example, as we mentioned, like slow and controlled release fertilizers, bioabsorbents that can be biodegradable, but anyway, they can gather the nutrients from wastewater, and then we can recycle back to use for the crop growth, and also food safety. So the packaging, the intelligent packaging films that can detect food spoilage as well, and other environment uses as well. So. Okay, I mean, I would like to thank this is almost my last University of Florida team, my students, visiting scholars, and postdocs. And here is my recent team, my 4 PhD students, and myself here. So, and also all the funding support from this year's from DOE, NASA, most of my funding from the USDA. Okay, I just want to use this nice picture to show. So what we're trying to do is using the nano assembly of bio-based waste or resource moleculars to achieve a beneficial circular bioeconomy. So I would like to take any questions.
Thank you. We have time for questions.
Thank you. It was a great talk. I have a question about your nanoparticles for drug release. Have you characterized the nature of the release? Is it sustained every time, or is there a burst release, or do you see systemic drug release throughout the model, or have you not done any in vivo work to test that?
For the drug delivery one, that one we didn't done like in vivo work, but for the nano-Chitosan one, I believe my collaborator definitely, I mean, they just directly feed the cows. Okay. Yeah.
So I noticed, excuse me, you're talking about a lot of your funding streams are from government agencies, but it seems a lot of the work also has commercial applications. Do you get, or is there commercial like companies or industry funding this kind of research?
Actually, I really got several patents based on my food safety project, and also my my fertilizers. But anyway, I mean, University of Florida did a very good job. We have the patent office. There are some companies contacted me, especially for food safety one. So there are several companies contacted me. They're trying to use my technology to build up like startup company. But I know it's so complicated. So I think I have my problem. I still want to keep doing like simplify this process, make it really can be commercialized. But most of my funding, actually, I got maybe some small funding from fertilizer company, But most of my funding is from federal agency. Like my food safety funding, first one we use the glycerol is firstly funded by the DOE because they're trying to see biodiesel process what the bio waste can use, and this and also I also got funding from USDA for this project. For the fertilizer one, we got funding. I think that one from the fertilizer company, and also the problem is like they are really interested in your really interested in your project, but they don't want to put any money. That's what the industry do. But I also got federal funding. I collaborate with Egypt, so we got it from NAS. So NAS it's not that much money, but but you can collaborate with the Egypt team. So you got a chance to go to Egypt for twice. So I think that's the benefit. So yeah.
Yeah, I had a question. The cycle of I guess renewables or recyclables is meant to be a circle, but a lot of times it's more like a spiral. So you go around once and it doesn't quite match up, and you end up with something that's a little lower quality. And I think you've done a good job in sort of repurposing something that was waste and have that go around the cycle again. But then you still have that mismatch at the end where the quality of whatever you're working with gets lower, and so you're just sort of delaying a waste stream. Have you figured out any way or working on any way to kind of close that and really make these? I think your last example where you are breaking things down to, essential nutrients in the soil kind of gets there, but in other cases you end up with, this modified Chitosan or this modified alginate that's still a waste product in some sense.
Yeah, probably. I didn't show some of recent work. So my recent work is like, we really got the waste materials. We make the materials, as I say, as wastewater treatment after waste treatment. So we got this one because all the materials I use is bio-based. So it's not harm like polystyrene, polyurethane. It's not like that. They can be easily biodegradable. Like for Chitosan one, that one is different case. Actually, that is called we made it's just like nano drugs. So I really don't know how my collaborator do for next work. So they just directly eat by the cow. At least the cow is safe, And we really use some, if you see, they really use some like wands to look at the toxicity, But anyway, for snow release fertilizer, recently people just use the sulfide, petroleum-based materials to make the coating materials. So what we do is like we made all materials is from even residues, and also like peanut shell. They are biodegradable. They are not harmful for the soil. Even like we did some work with some agriculture scientists. We use like biorefinery residues, cellulose, and lignin. Actually, they are really good. They are organics. They increase the organics of the soil. So they will benefit the soil. They don't have any harm to the soil. Yeah, you're right. We should do the life cycle analysis, or we need to. Yeah, that's important. But anyway, we definitely do some like biodegradability studies put in the soil. I don't know if I answer your questions. Yeah.
I have one question, maybe a little bit similar to what I just asked. And so in our world right now, we are more looking for the organic foods. So if we use the soil treatment with your fertilizer, and we plant agriculture, can we say that those agriculture are organic foods, or is it possible to be organic foods?
I really don't know much about organic food. So, but anyway, for the croppers, you can say, I think one of my students even did that. We add some like, for example, we add some metals that good for the people healthy. So into our, included in our control release fertilizer. So, I mean, then we look at the croppers grow, we look at these metals. So in that case, we can say we can really like for the radish, I don't know, maybe for the radish, like you can add some like nutrients so they can transfer through the fertilizer. You can transfer these nutrients to the food. So then, I mean, that can be say we got the organic food like that. So yeah. Oh, I think what you mean is like I know what you mean. So we can. You mean if we use this fertilizer, can we say we got organic food? I think we can, because you don't use you don't use the fertilizer from the chemicals. You know, maybe I'm confused. I mean, I never think about this problem. So, yeah.
I was impressed with the tensile strength you showed for the nanocellulose crystallites. And I was wondering then, when you moved to the gels that you formed, were they using those crystallites to form the gel? And if not, can you make gels using those crystallites and capture that really great strength?
I don't use nanocrystals, because what we do is like I still keep the amorphous. Nanocrystals is you remove all the amorphous phase. I mean, that is just very good example, you know, as a review materials. But anyway, I think you can add the nanocrystals into the gel. Yeah, definitely they can. I cannot say definitely, because when you form the film, so nanocrystal can increase the gel the gel strength. But if you use nanocrystal, I really don't know the answer, because maybe depends on your interbonding, right? For the gel, it's based on your interbonding. But a nanocrystal may be not good as like a microfabricated cellulose, maybe not that good interbonding.
So you were using water-soluble carboxymethyl cellulose that was then functionalized and cross-linked?
I mean, we previously made the nanocellulose. We look at the gel strength. We don't do any functionalization. But when we want to make the like the films, when we want to make the injectable gel, we functionalize that. Yeah.
Thank you.
Okay, I think we have one more over here.
Thank you for the talk. I was curious if you're using the bioresource materials, like if you showed cardboards, for example. Could you comment on the reproducibility of your experiments? Like, does it affect it? Do you have, if it's a different source of cellulose, for example, would you have different results when you're doing the same experiment or not?
That's a very good question. Actually, for some research, like for glycerol, so actually if you have impurities inside, definitely they can, because you need to tune your nano shells, right? Depends on different kind of chemicals you use, right? Definitely they can affect. But I think for agricultural use or maybe environmental use, I mean, it doesn't matter. We definitely directly use like peanut shell. I just got like shop some. We got like strawberry, like some biomass just from the waste. We started with that, like liquefy that, and then we put it together, coating material. So, I mean, there's no problem at all. So depends on how precisely you want to tune. You know, the problem is like that. If you use for the no value use, like snow release fertilizer or that, you really consider about your how much how much price you put, right, for your raw materials. But if you use for the drugs, for others, so maybe you can do better extraction, spend more money on that because you got more expensive products, more valuable products, yeah.
Great. Any last comment or questions? If not, let's thank our speaker one more time.
Thank you.